Now, when we look at the wave equation, it sounds a little bit funny. It sounds a little bit strange. We notice that the right-hand side, apart from delta x, it is the mass times the acceleration, right? So the left-hand side must represent the net force. Is that right? But the net force is sounds strange. It's proportional to the second derivative of u with respect to x, which is not the usual form of the net force, right? The tau is a tension. The tau is a tension force, but there's a strange factor here. The strange factor is the second derivative of u with respect to space, but not with respect to time. So this factor is quite strange. Okay, but how can we understand this factor? Okay, the tension tau is right, but we have a strange factor here. So what is the meaning of this factor? Why is the net force proportional to the second derivative with respect to x? Now, we can consider a special case to understand the meaning of this. Now, consider a peak in a wave. So at the peak of the wave, the first derivative is 0. Is that right? Because you have a horizontal tangent at the peak. So the slope is 0. So you have du dx equal to 0. And on the left-hand side, you have u increasing, right? So du dx is larger than 0. And on the right-hand side, you have du dx decreasing. So du dx is smaller than 0. Is that right? Now, so what would then be the second derivative? In your high school differentiation, in your high school calculus, you learn that if you have a peak, then the second derivative of u at the peak is more than 0. Why? Because you can now see, because the u dx is positive on the left and is negative on the right, and is 0 on the top. So you can see from you go from the left to the right, du dx is always decreasing. The slope is decreasing, right? At the peak. So that's why the second derivative of u is negative. And the second derivative being negative, it means the net force will be in a downward direction. It will be pulling this peak of the string back to the equilibrium position. So the larger you imagine now, if the second derivative is larger, then the slope is changing fast. The slope is changing fast means you have a very curved peak, a sharp peak here. If you have a sharp peak, then the tension force will be pulling you down with a larger force. And so that will cause you and give you a larger downward acceleration. When you have a more gentle change in the slope, if you have a smaller absolute value for the second derivative, then the downward force will be small. Okay, so that this second derivative actually gives you the curvature. It measures how curved the peak is at the top. If the peak is curved, very curved, and the peak is sharp, then the downward force will be large. If the peak is gentle, the curve is relatively smooth, then the downward force is small. It is that meaning. It measures how fast the slope change. If the slope is changing fast, then you have a large downward force. If the slope is changing gently, then you have a small downward force. Okay, so you now understand why there's such a factor. Okay. Now, in our discussion, we have confined ourselves to monochromatic wave. But in fact, you can actually prove, even for a wave which is not monochromatic, you can still prove that there are certain kind of general solution to the wave equation. And in fact, the general solution is given by a solution of this form. Okay, if the u is given as a certain function, now the function is complete arbitrary, so you can have a complete arbitrary shaped pattern. Okay, you can have a complete arbitrary waveform, as long as the functional dependent in x and t is satisfied this relation. F is not a function of x and t separately, but f is a function of x plus or minus vt, where v is given by this velocity in terms of the tangent and mu. If that is so, then I guarantee to you that this guy will satisfy the wave equation. Okay. Now I left the proof. I left the proof to you in your homework. You can write the derivative without much difficulty, and using this derivative, you can prove the wave this guy in this satisfy the wave equation. Now, how can I find the derivative of this guy? How can I find, for example, round u round x, say for example? How can I find this? Well, I just apply the chain rule. Again, I define this quantity to be C, the guy inside the brackets. Function I define the C. So I apply the chain rule, right? Is that right? Now, the first term, you notice that the first term is the derivative of f with respect to its argument. So I can define, in fact, I can just write as a total derivative. I can just define this guy as a first derivative of the f with respect to the argument. I write that like this. And the second term, d cos c dx, I just give you a 1, right? T is independent of x, so I differentiate with respect to x, I just get 1. So it becomes f prime cos c multiplied by 1. How can I find the derivative with respect to time? I do the same. I differentiate with respect to cos c again, and I differentiate cos c with respect to t. Again, I got the same derivative, because for both x and t derivative, d cos df, d cos c are the same, right? So it is straightforward differentiation of the function itself with respect to the argument. Okay, but the cos c dt here, we can have plus or minus v. Okay. Now, so you can proceed with one more differentiation to get the second derivative, and you will see the second derivative actually satisfy the wave equation. Now, the first derivative of f with respect to cos c, I denote it as f prime cos c. This is a definition. I can also denote the second derivative of f with respect to cos c as this, as f double prime. So in terms of f prime and f double prime, you can actually prove that this function, in fact, is a solution to the wave equation. It can, in fact, satisfy the wave equation. Okay. Now we discuss about the superposition of waves. Now in high school, you already have learned how the two waves superpose. Suppose you have a peak coming from the left, from the right, and another peak of wave coming from the left, and the two peaks collide with each other. So what will happen? The two waves are superposed to give you a high wave, right? But when the two waves bypass each other, when the peak A when the pulse A has become here, and the pulse B has become on the other side, the two waves just bypass each other, and you will see the shape will not change. The same wave as A is here, and the same wave as B is here. Okay, the shape will not change. Now, provided that there's no energy dissipation, we assume no energy dissipation. And if there's no energy dissipation during the motion, then the wave just bypass each other as if nothing had happened. Okay, so that is an interesting feature. Now we look at the superposition in more detail. Suppose we describe the first peak as U1 and the second peak as U2. When they superpose, at the moment when they overlap, the disturbance just adds algebraically to a larger value. So when the two waves superpose, you can see the resultant waves is just the algebraic sum of the individual wave. The total wave is just U1 plus U2. They just add up together. And when the wave bypass each other and when they separate again, they would not interfere with each other. U1 will not affect U2. The presence of U1 will not affect U2. And the presence of U2 will not affect U1, right? They still are just adding up together. They are not affecting each other. And the superposition of U1 plus U2 just gives you the total wave on the string. Now, the fact that the superposition will not affect individual waves lies on the fact that the equation, the wave equation is linear. It admits the two solutions which can be add up independently. Okay, U1 and U2 can be added up to form the whole solution without affecting one another. Okay. Now that is the principle of superposition. When the two waves superpose, the disturbance just add up algebraically without affecting each other. Now, but the point is, the so-called principle of superposition is not always true. Although it's so-called the principle, it is not something like a Newton's law or conservation of momentum, which is always true. And in fact, the principle of superposition is not always true. It depends on certain conditions. The first condition is that it depends on the nature of the waves. And the second condition is that depend on the amplitude of the disturbance. Now, for a taut string with a small disturbance, the principle of superposition is almost true. You can superpose the wave to give you a higher waves, larger waves when they superpose when they are overlapping each other. Okay, but that may not be the case for some other waves. Now, the linear wave approximation is actually a good approximation for many physical situations. For example, even if you are talking about electromagnetic waves, if you have one light beam traveling in this direction and other light beam traveling in opposite direction, and when they superpose, the light intensity just simply add up. The E field simply add up, and then you have the light intensity also increase. So even for electromagnetic vibration, the principle of superposition still hold. But this principle does not always hold. For some kinds of wave, which is called nonlinear waves, the superposition principle does not hold. If you are talking about gravitational center, for example, two black holes, very strong gravity center, that obey general relativity. If you have two black holes revolving around each other, and because of the revolution of the two black holes, they disturb the surrounding space-time to give you a gravitational waves. Those gravitational waves cannot be added algebraically. The gravitational wave obeys a complicated wave equation, which is not linear. So in general, gravitational wave cannot be superposed, just like ordinary waves. If you have one black hole, then you have a disturbance of space-time surrounding it, I call U1. And other black hole, you have a disturbance of space-time, I call U2. If you have two black holes present together, you cannot simply add up U1 to U2 to get the full solution. So that's why general relativity is so difficult. It does not allow principal superposition. You have to solve the Einstein equation again in the presence of the two black holes. Okay, and so the principal superposition is not always true. And also it depends on amplitude of the disturbance. Now we actually have made an approximation. I don't know if you have remembered that. When we derive the wave equation, we have made an approximation that the sine theta is almost equal to tangent theta. But imagine if the angle is large, then this approximation will fail. And also, if the angle is large enough, then the tangent tau will not be the same over the whole string. And all this approximation will fail if I go to a larger angle. So imagine if the disturbance on the wave is large, then all this approximation are going to fail. And we cannot have the principle of superposition anymore. So that means our linear approximation is only an approximation, which depends on the amplitude of disturbance in the case of a taut spring. Okay. So this is a general linear wave equation. If you have a wave described by this equation, then I can assure you that the principle of superposition will hold. Now, how do we prove it? Suppose U1, U2 are separately the solution to this equation. Then I claim that U1 plus U2 will also satisfy this equation. That means the superposition of the two waves can also propagate along the string, or along the medium. Now, so since U1 and U2 are the solution, we can separately write down the two equations using these two solutions, right? And we can simply add them up. And because the derivatives are distributive, the derivative separately acts on U1 and U2 inside the bracket, and also the same for the right-hand side, I obviously can see that the sum U1 plus U2 satisfies the wave equation. Okay, so U1 and U plus U2 is also a solution. Now, but this is not the case if the equation is not linear. What is called not nonlinear is that when there is a term in the equation which does not proportional to U, but proportional to higher power in U. For example, U square, du dt square, etc., or even U raised to square root U or something like that. If it's not power 1, then the equation will then be nonlinear. And for those nonlinear equations, you will see you can easily prove that the principle of superposition will not hold. Okay. Now suppose we have this equation. Okay. This equation is funny. Instead of just a linear wave equation, it contains another term, which is a constant alpha multiplied by the square of U. Now, so we can write the, suppose we have two solutions now. The two solutions are U1 and U2. So we can separately write the equation as in terms of U1 and U2 because both of them are solution, right? Again, we have U2 as a solution. Is all right. But when you add up the two equations, you find that U1 plus U2 is no longer the solution. Why? Because the derivative is still distributive. So you have U1 plus U2. That's okay. And you can, sorry, this is minus sign. And for the time derivative, is also okay. But for the nonlinear time, it's not okay. Because you then will have U1 square plus U2 square. But U1 square plus U2 square is not equal to U1 plus U2 square. Is that right? They are different by the term 2U1 U2. So obviously, if you cannot convert this term into this term, then U1 plus U2 is not a solution to the wave equation now. Okay, it's not a solution. So for this nonlinear wave equation, you cannot have the principle of superposition. And that means you cannot just superpose the two waves to find the solution when the two waves are present together. It simply does not work. Okay. Now, so this is what we said before. Many sources of nonlinearity actually can occur. Okay, in a real string, the tension tau may not be the same at all parts of the string, and the approximation sine theta equal to tangent theta may not hold for large angle. So linear wave equation is just an approximation for mechanical vibration on a string, and the superposition only holds for linear wave equation. but not for large amplitude waves, which obey a nonlinear wave equation. Nonlinear wave equations are more difficult to solve compared with the linear wave equation, but they are more realistic actually. And people usually solve that by numerical method. They do not use pen and paper to solve it. They use a computer to solve it. That is what we commonly use. We commonly do in our age of computer science. Now, having learned the principle of superposition, we discuss about the superposition of one-dimensional superposition of waves. Suppose we have two waves, looks like this. Now, these two waves have the same amplitude. The amplitude are U0. And both waves are traveling in the same direction. They both have the factor of kx minus omega t, right? So the both waves are traveling in the positive x direction. The only difference between these two waves is that the second wave has a constant phase phi. It's shifted by a constant phase with respect to the first wave. So we want to find out what will happen if the two waves propagate together. If the two waves are present together on the string, how would the disturbance change? Okay, so we simply add them up. Okay, now adding them up, simply add. We are concerned with adding a sign to another sign, which is of the different argument. Okay, the first argument is kx minus omega t. The second argument is kx minus omega t plus the phase. So I call this A, and this should be B. The two arguments are different. Now, so we have to rely on the so-called addition of trigonometric function formula. If you have a sine A added to a sine B, the result will then be 2 sine A plus B over 2 cosine A minus B over 2. Now, this formula, I recommend you to remember it, although I will not test you in the exam. If I test you in the exam, I will give it the formula. Okay, but if you are going to study physics or you are interested in physics, I recommend you to remember it. Sine A plus sine B is equal to 2 sine A plus B over 2 cosine A minus B over 2. Now, so the first term, sine A plus B over 2, is the addition of the two arguments divided by 2. 2 of this kx minus omega t divided by 2 is, of course, kx minus omega t. Phi divided by 2 is phi over 2, right? So we have this term. The second term involving the cosine has A minus B over 2. This is A, this is B. A minus 2, we get rid of the kx minus omega t because they cancel. So we have minus phi over 2. But the minus sign for the cosine doesn't matter. The minus sign simply gone when I take the cosine. So I have the term of cosine phi over 2 here. Now, cosine phi over 2 is a constant. It does not depend on x, either x or t, right? So I can put it together with the amplitude. So this becomes the new amplitude of the waves. And this term goes as sine kx minus omega t, which is a traveling waves. And you can see the frequency and the waving does not change. They both are the same as the original wave. So the superposition of the two waves result in a new wave with the same frequency and the same wavelength. The only difference is that there's a phase and the amplitude is modified. The amplitude has changed because the two waves superpose. Now let's see how the amplitude change. The amplitude actually depends on the angle. If phi is 0, cosine is 1, right? So I got the maximum amplitude at 2 U0. This is the maximum amplitude that can be attained because the maximum value of cosine is 1. So the maximum amplitude, that resulting maximum amplitude is 2 U0, which corresponding to the phase angle equal to 0 or 2 pi. If the phase angle is equal to pi, then this term becomes pi over 2. Cosine pi over 2 is 0. And I got a 0 disturbance. So the minimum value for this disturbance is 0. The maximum value for the disturbance is with the amplitude 2 U0. And for other angles of phi, the amplitude will be in between 2u0 and 0. Now, how do I understand this? I better look at the picture. If the phase angle phi is 0, that means the two waves are in phase, right? The two waves are just the same, right? The same waves. So when they superpose, the two waves simply add up to give you a larger wave. If each of the waves have the amplitude u0, then the resultant wave have the amplitude 2u0, which is this case, right? And this case is the what? Is a so-called constructive interference. The constructive interference we learned in high school. The two waves simply overlapping in a crest or trunk, so they add up to give you a larger waves. Okay, they are completely in phase. Now, this is a one-dimensional example for constructive interference. Okay, we will discuss two-dimensional example later. Now, how about when phi is equal to pi? When phi is equal to pi, then the two wave is pi out of phase. It's half of a wavelength out of phase. So the peak of the one wave will be superposed with the trunk of the other. And they always result in zero disturbance because every point, the two waves are of equal magnitude of disturbance in the opposite direction. So they always cancel. And that result in a zero disturbance. And that will become the so-called destructive interference. Okay, destructive interference corresponding to two waves superposing with half a wavelength out of phase. And half of wavelength correspond to the phase angle pi. Okay. Now, if the angle phi is between pi and 0, if it takes on other value, for example, 2/3 pi, then you will see a pattern like this. For example, the two waves is not totally superposing each other, and it's not totally canceling each other, and that will result in a wave with the same wavelength and frequency, but the amplitude is somewhere between 2u0 and 0. So this is a superposition. Okay, so this is a general superposition. And in fact, the amplitude is given by this factor. You just substitute phi equal to 2 power of 3 for this situation, and you can calculate this amplitude. Okay. Now, we better stop here today because we still have the